Alright guys, so welcome back. We're continuing with 12.2 and these are going to be more specific examples to kind of help you unpack what we just ran through real quick in the notes. But we're going to look at transforming with powers first and do a couple of examples, and then we'll look at transforming with logarithms and whatnot. Alright, so it says, imagine that you've been put in charge of organizing a fishing tournament in which prizes will be given to the heaviest Atlantic Ocean rockfish caught. You know that many of the fish caught during the tournament will be measured and released. You are also aware that using delicate scales to try to weigh a fish that is flopping around in a moving boat will probably not yield very accurate results. It would be much easier to measure the length of the fish while in the boat. What you need is a way to convert the length of fish to its weight. So because the length is one dimension and weight is dimensional, like volume, we cube the x length to make the scatter plot linear. And so this is original. You can see how if you were to continue it out this way, you could potentially see a horizontally stretched or vertically compressed cubic function. And if you transform it, it looks much more linear, right? And so this is length and weight. Well, instead of it being at 8 cubed would give you a point over here, and so on and so forth, all right? So another way that you can transform the data to achieve the linearity is to take the cube root of y, and so it looks very similar. It's not the exact same just because of rounding and whatnot, but you can take length versus the cube root of weight, and that would also appear very linear. So to see which transformation fits better, you look at the r squared, you look at the s. So you want to look at the standard deviation so that we can see what is smaller standard deviation would be better. An r squared closer to 1 would be best, and the residual plot. So you want to see that there is no pattern whenever you graph these things, all right? So a more general way to transform power models is by using logarithms, which is more efficient because we don't always know what power relates to two variables. And so if it wasn't, in this case we knew that it was cubic, but sometimes you don't know if it's x to the 5th or x to the 7th. We do know that it's odd, or sometimes if you can see the continuation, or even. But even so, if it's half of a quadratic, you can't tell the difference, and so there is some element of unknown. And so if you use a log, then you don't have to worry about it. All right, so this is the output, the computer output of both of these here. So we're comparing the length cubed and the weight, and also the length and the cube root of weight, okay? And so when we look at length cubed to weight, it has a constant, and it has the length cubed here, all right, and the standard deviation and all that. So let's see if we wanted to give, I'm going to split it up this way, that way you have length cubed weight on this side, and then you have the length cube root of weight. And let's see if we can come up with our equation. So remember that weight is our y variable, that's what we're trying to find, right? And that's going to be equal to, our constant coefficient goes first, so that would be 4.066 plus, this is our slope here, if you remember from what the computer outputs looked like before. So we have 0.015 if we round to the third number after the decimal, and our x that we're using is length cubed. Okay, now same thing with this one over here. We have that the cube root of weight is equal to, in this case, our constant is negative, so negative 0.022 plus our slope 0.247, and then our x value is the length. All right. So we have our y-hats, we have our constants, we have our slopes, and we have our x variable. All right. So we could use this to estimate either way, right? So if we wanted to use this, if we know that it's 36 centimeters long, then we just plug it into the length on either equation, and we can compare and see which one we get here. So if the length is 36 centimeters long, then we have the weight, our estimated weight, our weight hat, is equal to 4.066 plus 0.015 times our length, and we have to cube it because that's how it is here. All right, and so that, if you type that in on your calculator, you get 688.9 grams would be our estimate. Now if we use this equation here, then take the cube root of weight is going to be equal to negative 0.022 plus 0.247 times 36, and because we still have the cube root, we have to make sure that we cube both sides after we calculate this. So we get 8.856, and now we're going to cube both sides. So we get that the weight is equal to 694.6 grams. And if you think about terms of grams, being 5 off from each other is a pretty close estimate when looking at the weight of a fish. All right. So if we didn't know the specific power relationship between these variables, we could use a log transformation and take the log of both sides. So let's take a look at that. So we have Gordon Moore, one of the founders of Intel Corporation, predicted in 1965 that the number of transistors on the integrated circuit chip would double every 18 months. This is Moore's Law, one way to measure the revolution in computing. Here are data on the dates and number of transistors for Intel microprocessors. So we have the data here, and this is what it looks like. All right. Now you can do a scatter plot of the natural log, log base E, or natural log, okay, of the number of transistors on a computer chip versus years since 1970 is shown. Based on this graph, explain why it would be reasonable to use an exponential model to describe the relationship between transistors and years since 1970. So what we've done is we did not change the years here, so this would be an exponential model. If you look here, you can kind of see how that's exponential because it starts off very, very slow. And if you remember, things like doubling is what it said, I believe, up here, doubles every 18 months, and we know that doubling is exponential. And so what this is x in natural log of y is the relationship model, or the relationship we're modeling. So this is an exponential model. And we could say if an exponential model describes xy, then the relationship between x and natural log of y would or should be roughly linear. So the exponential model seems appropriate. All right, right, so here is the output here. So we have, this is your B, or this is your A, this is your B, and remember that it's y hat equals A plus B x. Well, we're using this relationship here, so it's really the natural log of y hat equals all that. So we have x and natural log of y still, and so the natural log of, and our y variable is the transitors, so we'll use that word here, make it our hat, just because this puts it in context, and that helps whenever you go and try to interpret things, and it also clearly communicates that you know what you're talking about to the graders. And so we have 7.0647 plus 0.3658 times years since 1970. And there's our equation. So let's now use that to predict how many transistors on an Intel computer chip in 2020. So 2020 is how many years since 1970? So 2020 minus 1970 equals 50 years. So this is our x, okay? And so we have the natural log of transitors is equal to 7.0647 plus 0.3658 times 50. All right, and then we have the natural log of our transitors still is going to be equal to 25.3562. Now, here's the deal, is you have to remember your different exponential rules and things like that. So to get rid of a natural log, you have to raise both sides, or you have to make e the base of both sides and raise both of these. So we have e to the natural log of the transitors is equal to e to the power of 25.3562. So now e and the natural log here cancel out. And so we get the transitors hat is equal to 25.3. Oh, this is still e, sorry. Is equal to, if you type this in on your calculator, you get 1.028 e to the 11th, or move the decimal place over 11 times, and so that would be 1.028, and then that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we get 102.8, and this would be billion. Alright, and so your answer is, yeah. Okay. Right. Last page of examples, and then we will wrap this up. Alright, so a residual plot for a linear regression in part B is shown below. Discuss what this graph tells you about the appropriateness of the model. Alright, so do you see a pattern? If you see a pattern, that means that this is part B is the transformed. Alright, so we see kind of that there is a little bit of a pattern here, okay? So we would say there is a pattern to the residual plot. Now if we look at this, the furthest one away is 1, Okay, this is, and here would be the other furthest one away. So, but we can say that the residual values are small relative to the y values. Because if we're talking about billions, then having it off by 1 is really not that far off, even if you see a pattern. All right. So the scatter plot of the transformed data is more linear, so we feel fairly comfortable making predictions. All right. So this is going to be our last example, and then we'll be done with some examples before we talk together on Friday. So what's a planet anyway? On July 31st, 2005, a team of astronomers announced that they had discovered what appeared to be a new planet in our solar system. Originally named UB313, the potential planet is bigger than Pluto and has an average distance of about 9.5 billion miles from the Sun. Could this new astronomical body, now called Eris, be a new planet? At the time of the discovery, there were 9 known planets in our solar system. Here are the data on the distance from the Sun in astronomical units, AU, and the period of revolutions of those planets. So we have our distance versus the period. Based on the scatter plots below, explain why a power model would be a more appropriate description of a relationship between period of revolution and distance from the Sun than an exponential model. So we have distance versus the natural log here, and we have the natural log versus the natural log. So we have taken the natural log of both sides versus we've taken the natural log of just the residual, and if you, or not the residual, the output, okay, or the response variable. So remember that here we take the log of both sides of its power. If you take the log of one side, then that would be an exponential. All right. So if we look here, this is not linear versus this is fairly linear, right? There is a strong linear positive relationship. All right. So this here is the graph of x versus the natural log of y, which is an exponential model. This here is a graph of the natural log of x versus the natural log of y, which is a power model. Okay? The exponential model is more curved than the power model, which shows a roughly linear shape and is thus more appropriate. So we want to use our power model here. Okay, so here is the output. All right, remember this is your A, here's your B, and we're looking at, we're going to use the power, so that means it's the natural log of x and the natural log of y. So we get the natural log, and our natural log of x is the natural log of y, because we're doing y hat is equal to a plus bx. So our y hat here is the natural log of the period, is going to be equal to 0.0002544 plus, we now have our b value, the 1.49986, 6, and we're going to multiply that times the natural log of the distance. I'm not writing on a space, but you get the idea. Alright, so here is our equation. We've defined our variables, so we're good. So if the data is not transformed for you, you can do it by doing the equal cell like I showed y'all in the other. There's more in the instructions in the book if you didn't fully follow what I was doing, but we'll do some examples together on Friday. But y'all have a great day.